It's running, yeah? Okay. Cool. Well, thanks everyone for joining. Yeah, so I mean, we're smaller crowds. I would say if you have any questions, just feel free to ask. We can have a bit of a discussion, like interrupt me. I think that could be nice. So I'm here to talk today a bit about technology and trading. So how technology has transformed trading, and maybe to start a bit about that, let me introduce myself first. So I'm Julian. I'm a software engineer at Optiver. I've been with Optiver for 4.5 years. I joined initially as an intern, and I studied computer science in Germany, and then pretty much did an internship there, and then joined full time, and have been there ever since. And yeah, I like it a lot. It's a lot of fun. Fuck! People don't see. Okay. That's a good one. Okay, let's
Today in demo effect we have you're on.
No, don't worry. Okay. Cool. Then, yeah. I'm Julian. Maybe I can move this over here. So like I said, I'm Julian. If you have any questions, please just ask. So yeah, pretty much the agenda that I broke this down into is to kind of first start talking about why technology in trading. So what is the role that technology plays? And I'll talk a bit about the history, like where this all started, because this is not something new that just happened over the last 20 years. It existed 400 years ago. We'll talk a bit about technology today, and sort of then what it takes to build a state-of-the-art trading system. So what do we actually do in the real world today to trade? And then I'll talk a bit about the future, and then we have a bit of a Q&A session at the end, if there's some time left. That's the rough idea. So, I think ultimately trading is all about a race to transmit information. Whoever knows something before somebody else will have an advantage. Right? If you buy stock and you know that, I don't know, it's going to go up for whatever reason because there's some news release or something like this, right? It's better to know first than to be the last, because then the stock will already have moved. All right, so to illustrate this a bit, right, let's say we bought some Tesla shares here, and our friend Elon starts to tweet that in his opinion the Tesla stock is too high, and you own some Tesla. What do you think you should do?
Wait if he is something happens.
So you would wait, okay. You would. Anybody else?
Elon Musk is pretty good.
Okay.
Probably I will sell.
You will sell. So imagine, right? Everybody, you can wait. But if other people start to sell, then the price might have dipped by 5 minutes later. And then you might have lost some money on your activity. So whoever knows this first, will have an advantage. Pretty much whoever sees this tweet first will know, oh shit, like if this guy who owns the company thinks his company is overpriced, maybe that's not a great sign. And so whoever sees this first has an advantage. And that's true, today as it was true 400 years ago. So it's a funny story where pretty much, with the ships used to sail between the Atlantic, between the US and Europe, people would look and then see like how much cargo was on the ship. And depending on how deep it was in the water, they would sort of speculate how that would impact prices when the ship arrived. And then pretty much they would trade on that. So that's pretty much, already then 400 years ago, sort of the same story existed, just not with modern technology. So yeah, that leads me to talk a bit about the history of trading, like where this all started. And I think to kind of to start, we have to talk a bit about where a stock comes from, what a stock really is. Right. So a stock is a share, so if you want to buy a stock, you're essentially buying a small chunk of it. And how this came to be was that stocks were actually rented in the Netherlands, in Amsterdam. Right, we had the Dutch East India Trading Company. So this was sort of during the Dutch Golden Age. They were trading a lot, and to do more trading, to grow their business, they needed more ships. Right, the ships are expensive, and so they cost money, and they didn't have the money to build ships. And so I had this idea: what if we offer people something, and then they give us their money, and then we use their money to build more ships? And this something was sort of a chunk of their company, so that you could buy the stock, which was a piece of paper, and then 10 years later, you would get a share of the profit that the company made. And that was sort of the trade. So you give them your money now, they grow it, they grow the business, and then 10 years later, you would hopefully get something more valuable in return because the company would have grown. So 10 years is very long, right? Like nobody really thinks today wants to buy something and wait 10 years. And they also realized this. So they came up with this idea that you can actually trade these pieces of paper. And they're not bound to you for 10 years. And that was the invention of the stock market. People could buy these pieces of paper and trade them. And that's how the first stock market was invented. And then pretty much, I already talked a bit about the telescope we saw earlier with the ships. There were a series of inventions, across history that led to more efficient markets. I think the telescope is the first big one. So before the telescope, people would see how deep the ship was in the water. And after the telescope, they could actually see the ship and they had a better estimate. So that was helpful. And then they had at some point they invented these optical telegraphs, which was you can see these things here, and they could orient them in different ways. Depending on the configuration, it would mean a different thing. So they could transmit information visually, like from hill to hill, maybe. I don't know if you're a Lord of the Rings fan. In Lord of the Rings, there's this moment where they light these beacons, they put them on fire. It's sort of the same concept. But yeah, the biggest technology that sort of changed all this was the invention of the transatlantic telegraph. Right? So this is sort of near real-time communication. It still took 16 hours to transmit a 98-word message, right? So this is not like today where you just send a text message and it worked. It still took a long time. Why do you think it took 16 hours? And why was it not instantaneous to send a message?
Through sound.
Sorry?
It was sent through sound.
It was sent to what?
Through sound.
To sound. It was sent to wires. So they had cables in the ocean. It was sent electrically.
They had to decode it then?
Yeah, they had to decode it. So I think the biggest reason is that there's a lot of noise, a lot of errors. So they would send a piece of information, and then they would have to make sure that it was the right information. Like they didn't have all these error checking things that we have today. right? They would just send a signal, and most of the time it was inaccurate, and then they had to like go through this complicated back and forth to make sure that the message they had sent actually is the message they expected. And so yeah, it was quite long. It took 98 words, it took 16 hours, but still better than 3 weeks, you know, that it took to sail through the Atlantic. And so, and this is also not something that happened overnight. You can see, like, this took 7 years to develop. You can sort of see how, like, this is the evolution of the cables that they used. The very first cable was like this. It worked for 2 weeks and then it broke. They laid across the Atlantic. And yeah, they tried to iterate and come up with, you know, better and better cables. In the end, the final cable that didn't work, they had to actually build on the ship because it was so heavy it would break itself, you know, under its own weight. They had to assemble the cable on the ship, and then pretty much as they were assembling it, they were putting it in the water. And yeah, and then that was sort of the birth of the telegraph. And I think this is maybe one of my favorite slides. You can see the impact that the telegraph had on sort of prices of goods before and after. So the telegraph was invented here. So before the invention of the telegraph, you can see, so this is the difference in price between, it says commodities, I think it's cotton here. So it's a difference in price of cotton between New York and Liverpool in the UK. So sort of the difference in price that we pay in each location. And before, you can see like there are major fluctuations. And afterwards, like the price is a lot more stable. Does anybody know why this happens?
Because transactions happen more like reaction factors.
Any other thoughts? That's definitely one reason.
You can adapt to the market without any settings.
Well, there was still the 16-hour latency, but yeah, much less latency than the 3 weeks than before.
Maybe people from Liverpool saw that cotton was cheaper in Europe, so they buy it from there, even though it would take longer to arrive.
Yeah.
So maybe before the telegraph, they mostly work on guesses. For example, they knew that there was a price, and then they would receive the next price in 3 weeks.
Yeah.
They had to guess what would be the price. So for example, if they knew that it's higher than 3 weeks time, maybe they thought, okay, in 3 weeks probably it's even higher, and then increase this.
Exactly.
But when you receive information that your guess was incorrect and it happened in 3 weeks, then you have to say.
Yeah, that's exactly right. So pretty much, you had those buyers and sellers that were massively out of sync before because they couldn't communicate. They got price updates every 3 weeks, and you know maybe the last one was expensive, and they thought I was going to keep going up, but something happened, and now it was cheaper. And pretty much, yeah, it caused a lot of inefficiencies. And pretty much when demand and supply essentially was able to get more in sync, and which made markets much more efficient. So there was a study done that estimates that sort of this invention alone was an equivalent of an 8% increase in export. So pretty much they were making 8% more money, or it was 8% more efficient of all the goods that we're exporting just by having this faster communication or more efficient communication. Which I mean, if you think in terms of GDP grows by a couple percent, 1 or 2% per year, I think. So this is quite big. Yeah. So there's some more inventions along the way. You have a stock telegraph ticker. I don't know if you've ever heard of a stock ticker. It's usually what we call the symbol of a stock that's traded. That comes from this invention. That's pretty much. So this thing was connected to a telegraph and would just print out stock prices like on paper. You have a telephone, which I mean you can imagine it's a similar story as a telegraph. You have better communication and with voice and everything. And then I think another interesting one is also this quadruplex telegraph thingy here, which before this there was no continuous trading. You had auctions twice a day, and that was it. And because they couldn't trade enough information. But after this, they could actually have a more continuous trading. So people could sort of what, I don't know if you're doing our challenge, but if you are, you can insert these bids and asks into the order book, right? And it's continuous. So that's sort of the fact that they could send more information in this quadruplex telegraph method, could be continuous. Quadruplex, by the way, means that they can send 4 signals at the same time through the wire, not just the loop. So that's a bit about the past, right? And of course, I didn't talk about computers here, but I mean, computers obviously are very important. That's what we're going to talk about now. So, how fast was information transmitted today? That's a question we want to answer. Maybe to answer the question, we can talk a bit about what I'm going to say modern trading system looks like. So this is how we depict an exchange and trading from happening. So pretty much you have this temple here. For some reason, we always have a temple. I don't know why, but that's the graphic we use. This thing here is the exchange, and it has 2 sort of information feeds. The green is info, and this is anything that's happening publicly on the market. So when there's an order book update, like when the trade happens, so any public information that people receive is this green info line. And then this red line, execution, is our own private messages. So when we decide we want to make a trade, we send an order. It's a private message. We send it to the exchange. And if we get the order, then we get a trade. So this is the red thing. All right, so pretty much what happens, the exchange, let's say, sends out that there's a trade that happened in the markets, it arrives at at our computer, it goes to the network card, it gets loaded into memory, into the cache, right, and the CPU does some computation. Then we decide, do we want, based on this trade that just happened, do we want to do or trade ourselves? If yes, then we kind of create our own trade message or order message, goes to the cache, goes to the memory, gets flushed to the network card, and then we send it to the exchange. Yeah? So pretty much that's more or less how computer works, how we trade with a computer. And this is the bit that we can program here, right? So we can control what's in memory, what our CPU does. What do you think the latency is that it takes? Like, sort of in software here, how long does this loop alone take? Any ideas? Milliseconds. Sorry?
Milliseconds.
Milliseconds, yeah, I mean, that's definitely not wrong. I think we're a little bit faster than milliseconds. But yeah, so I think a good estimate is something like 2 microseconds. That's about as fast as you can get it usually. Maybe if you really squeeze it 1 microsecond, but like it gets difficult from there on. So that's sort of the latency range that we're talking about. So the thing is, right, how fast is fast, right? Like this millisecond, microsecond, what does that even mean? So to just put this into context, blink of an eye is roughly 300 milliseconds. Right? So you blink your eye about 3 times a second. Or you can blink your eye 3 times a second. If we look at the time it takes the light to travel 500 kilometers, that's about 16, 17 milliseconds. And that's also coincidentally the same time that it takes a game to run its loop, right? So if you ever played a computer game, the internal mechanism of a computer game is like the time it takes, to process the input, to update the game state, and to render the frame. It's also in that range, like 17, 16, 17 milliseconds. If you stand at the top of the Eiffel Tower and you shine a flashlight on the Eiffel Tower, the time it takes the light to hit like the bottom, that's roughly 1 microsecond. So the time it takes for light to travel from the top to the bottom of the Eiffel Tower is one microsecond. So if you think back to the computer algorithm, that's about twice as slow. Right? So that's like light going back and forth, up and down the Eiffel Tower. I always think it's pretty crazy when you think about it in these terms. And it doesn't stop here. If we think about how long does it take light to travel for 1 meter, something like this, a fiber cable, that's 5 nanoseconds. So light travels 5 nanoseconds in a fiber cable. So just to put this into perspective, 5 nanoseconds, that's the equivalent of 200 million eye blinks a second. So the time from the mirror, you watch yourself blink 200 million times a second, that's 5 nanoseconds for you. So back in 2017, a colleague of mine, a former colleague of mine, Carl Cook, he gave a talk at the CVP-Con about something similar about building trading systems. And back then they were saying, okay, the best time for latency for software is like 2.5 microseconds that it takes to build a software trading system. And then he used the Burj Khalifa as an example, like the Eiffel Tower. But then, if you fast forward a little bit, so this is already a year old now, about a year old. So this is a picture published by the Frankfurt Exchange, and they are one of the most competitive exchanges in the world, where people compete most for latency. And you can see a heat map here of how long pretty much people's trading systems take. And this is measured in nanoseconds. You can see this here. And these red dots is pretty much where market participants fall. So you can see in 2019, people's trading systems were something like maybe 100 nanoseconds. And then in 2020, it sort of below 100 nanoseconds, and then it keeps going faster and faster. And like now here, right, it looks like we're almost at zero, I don't know, maybe 15 nanoseconds. So just to repeat, so this is the time it takes from the moment where the exchange sends out a piece of information to the moment where they have received your reply. So that's something like, I don't know, 15 nanoseconds. And if you think back, that's the equivalent of like 3 meters that it takes light to travel in fiber. So literally in these 3 meters of distance that light travels, that's how fast some systems, like in the world, react and send out trade. So the question is like, how is this achievable, right? And I'll answer that question in a bit. So, and I think, pretty much, right, talk a bit about the challenges that we have today. One thing is we have to build fast systems. And I always like to say that it's two problems, or 2.5 problems. So we have to build fast systems, but we also have to build smart systems. And what do I mean by that? So what is, and we have to do both. So I'll explain in a moment what exactly that means. So what is a smart system? Maybe let's start with that. So smart system, right, it consumes a lot of data. Usually like there's a lot of data science, machine learning. It has terabytes of just various data it consumes. It's complicated, it's multi-layered. It's just slow, right? Because it's complicated. It has to do a lot of computations, and then you have to do a lot of computations. It just can't be that fast. So what is some data that flows into sort of a smart decision, let's say? Right, so you put your Bloomberg is one, right? Stuff happening, people tweeting. Just stock price information on exchanges. We also talk to brokers on phones. That's also information on a process. That also matters. Of course, internal data, so like stuff we compute ourselves, analysis that we do, that also is, flows into these smart decisions. And volatility. I don't know if you've heard of volatility, but that's how much stock prices move up and down. And these are just some of the ideas that I wrote down in 5 minutes. Like, I'm sure there's way more, but this is just sort of some stuff that I came up with. So, sort of the idea of a smart system is that it's able to make a good decision, right? It sees what's going on in the market, it doesn't just do anything randomly super fast, but it sort of sees the big world and makes a smart decision at that point in time. But to do that, you need to consume a lot of data and you need to do a lot of computations, and that means that it's complicated and slow. But at the same time, you have to be fast. Right? We saw this slide earlier of how fast people are. So how can you sort of do all data analysis and be so fast that you react in like 15 nanoseconds. So this is sort of a bit of a conundrum. And that's, I think, the challenge that we're solving, that we're building things for. We have to build systems that are smart and fast. And that leads me a bit to talk about modern trading system. How do we solve this problem? How does this actually work? So you saw this slide. That's a bit about how a software trading system works. And we talked about this, and we saw, okay, man, people are way faster than these 2 microseconds. Like people can do this in 15 nanoseconds. So how do they do this in these 15 nanoseconds? The answer to that is essentially what we call custom hardware. So these are computer programmable chips, they're called FPGAs. Stands for Field Programmable Gate Arrays. Has anyone here heard about an FPGA before? Yes, some people. So pretty much an FPGA is a computer chip that you can put your own electrical circuit on. So you're no longer writing code, but you're designing an electrical circuit that gets printed onto the chip, and you can reprogram this chip. You can reconfigure these circuits pretty much with software. So you don't need to print it. You don't need to build a new chip yourself. You can reconfigure the chip. And this allows you to be quite fast, because essentially it's like having your own dedicated CPU, and it's slower than a dedicated chip, but you're still way faster than software. And that's pretty much how you get to these 50 nanoseconds, because you just send a signal in and then you send the signal back out, and there's almost no processing. So when you use an FPGA, it looks pretty much like this. It's like what I just said. So you receive, like, let's say this trading happens on the exchange, it goes into the FPGA. The FPGA does some computations, decides, hey, do I want to react on this? It's pretty much just like a bit-by-bit comparison. And there's, bit number 27 that says, okay, now I want to do a trade, and it just sends out a trade message that is also pre-computed. And that's a bit what an FPGA looks like. So this is like a scan or an image of the logic on the chip. So this here is the chip together, and these are sort of blocks. It's a bit like a floor plan of the chip. So sort of like like an architectural plan of a building. This is the same thing for a chip. The different colors that you see here are different logical units that are built on the chip. And what's interesting is that only this area right here, so only the highlighted area is where the actual trading happens. So we have this chip here. We're only using this very little piece of space to do our trading, and that's very intentional, right? Because the bigger the logic, the longer the path, and the bigger the computation. But if it's just here, then we save space and everything gets a lot faster. So we really just want to, even at this level, we want to minimize how much space we need, how long things take, and that's why we're only using this little part here. And I mean, maybe to give you an example of what this might look like, right? So let's say this purple thing here is maybe what reads the exchange message. This green bit is then what decides, okay, do we actually send a trade or send an order based on this exchange message? And then maybe the red and yellow is like the thing that actually sends it. I'm just making this up. I don't actually know what the colors really mean, but it could be something like that. So that's a bit about an FPGA. So that's how you get these crazy latencies. But that's pretty much on the computer itself, right? Like that's once you receive the message and then you send it back out. But sometimes maybe the exchange is in a different data center and you have to send messages, across the world or across land. And so it turns out that if you send light to fire, it's actually slower than if you send it to vacuum, because the light bounces inside the fiber cable. And you lose something like 30% roughly of speed. And so if you use microwaves instead, you're faster than if you send it to the fiber cable. So microwaves are just like these big, massive towers. You can see them here, and they just send signals to each other, and that's how a lot of communication gets done in the trading field. So there are these microwave towers, and we send information across countries. And it's actually quite funny because it's in the air. It's very unstable, right? So let's say there's some birds that fly by that can disrupt your signal, and suddenly you don't get your message. So like the cable is very reliable, but these microwaves are absolutely not. And so usually what we do is we have redundant fiber cables underneath, so that if our message gets scrambled because of bad weather or birds or whatever, we still get the data. I wanted to give like a example of how this really matters, like how sensitive this problem is. So I think the most competitive sort of trading route in the world is between Chicago and New York in the US. So pretty much the US has the S&P 500, which is the biggest US index. So it contains the biggest 500 US companies. And pretty much this index gets traded in Chicago. But there's a thing called options, which is a very correlated product. It doesn't really matter what it is, but it's a big thing. And this gets traded here in New York. And it's very, very correlated. And so what this means is that the information of the trading that happens in Chicago is extremely relevant when you trade this stuff in New York. And so whoever can send this information fastest from Chicago to New York will have a massive advantage. And you can see here, like these little points, these are data centers in New York. So pretty much New York is right here, somewhere, and then this is New Jersey. And this like NY5, NY4, NY2, Carteret, MAWA, these are all data centers, essentially. They all receive data from Chicago. And the distance here is roughly like the distance to NY4, I want to talk about NY4 and NY5, is 1,250 kilometers. Yeah? But it turns out that if you're NY5, you're roughly 1.5 microseconds faster than if you're in NY4. And that's because NY5 is 400 meters closer to Chicago than NY4. Yeah, so you're literally like, it's across the street. It's 400 meters closer to Chicago when you're standing in New York. But the fact that like, these 400 meters make a difference such that you're suddenly 1.5 microseconds slower if you're in the wrong data center. So if you start to build your trading system, if you decide to put your computer somewhere and you choose the wrong data center, you've already lost the race. Because there's nothing you can do, you're in the wrong data center. You're going to get information 1.5 microseconds slower than everybody else that's in the right data center. So I think it's just to illustrate a bit like how we think about these problems. We don't just write code and deploy our app, but we really think about like every layer and like what actually happens in the real world with sort of the code that we've written, right? Like if we know that we're going to deploy a trading system here in NY4, we also know that it can't be as competitive as somebody who is in NY5. And maybe we put less effort into optimizing this. Whereas on the other hand, if it's in NY5, we put more effort. So that brings me to talk about how do these co-locations or how do these data centers look like? We call them co-locations. Co-locations because, bring back, co-locations because we're usually co-located to the exchange. So wherever the exchange has its data center, we're in the same data center. And so pretty much in movies, data centers, usually look like this. I think in reality, it looks a bit more like this. It's not quite true, but it's a bit more messy than it looks in reality. But it's not that far off. Right, so the point is we experiment a lot, we try things, we always play around. And that's why it's not as clean as in movies. Like we pretty much are always experimenting and trying to come up with something more competitive. And I have been to data that looks like this. It's not totally crazy. So what does it actually look like? Right, when you build out your co-location or your data center, you have to optimize sort of the setup externally. When you have power budgets, it's a bit like if you ever build your own computer, you know, you have a power supply and you can only hook up as much as your power supply gives you. And it's the same here. We have a power budget and we can only put in as many computers as there's power. So you optimize for that. You optimize for cable lengths and distances to the sort of microwave receivers within the data center. So you want to be closer to the microwave, you know, the microwave receivers rather than further away. The more competitive stuff you want to put closer to wherever you get the cable from the exchange and not further away. And of course, I mean, when we talk about all these time latencies, we need a way to measure them, right? Like, how do we know that something is 5 nanoseconds or 10 nanoseconds or 20 nanoseconds fast? Right? It doesn't. If you don't measure this, then you don't know. And so you need very, very precise measuring to be able to figure this out. And so we use a technology called the White Rabbit for this. This was initially developed by CERN, the particle collider in Switzerland. So they have a sort of similar problem where they do these particle collisions and they want to have extremely precise time measurements of when these collisions occur and how these particles move in space after the collision. So they have come up with this technology called the White Rabbit, which achieves sub-nanosecond accuracy on measuring timestamps. And it's open source sort of hardware and software. So the trading industry has adopted this technology that they've built for our own purpose to measure pretty much trade latencies. And so that kind of brings me to this picture of the full stack. How we think about this problem. So in the co-location, the data center, we have our FPGA, but we also have software trading strategies. And FPGAs are fast, but they're very expensive to build. We're not going to do this unless it's really worth it. And so like 95% of our stuff is in software because that's just way easier and scalable. And so unless if you don't really need this latency, we don't usually invest in this either. If you have this FPGA, you also need all sorts of control systems that control the FPGA. And so the FPGA is, in some sense, very complicated, but also very stupid because it will just compare bits and send out a message. It does not have any kind of a smart system. So you need some sort of smart systems here that tell the FPGA when to actually make a trade, under which conditions to make a trade. Same with like a pricing system. So you need to come up with prices, you need to compute accurate prices, and you need to come up with all the things that are happening in the world. And if you think back to the data I was talking about earlier, Bloomberg, etc., you need to take it all into account and come up with a fair price. And yeah, by the way, I didn't say this, but pretty much as we migrate, so these are like sort of fast but dumb systems, and these are like slow but complicated systems. And the data that these slower systems compute feeds into, it's like pre-computed data that feeds into the fast systems. And then the fast systems just act on the pre-computed data. And that's sort of how this fast and slow, or fast and smart problem gets solved. By having pre-computed smart data that the fast systems just act on it, sort of cache. And of course, the risk system is also quite important. I mean, if you're trading at these latencies of, I don't know, milliseconds or microseconds or whatever, or nanoseconds, then it's quite important that you also are able to monitor yourself at that latency, right? You don't want to bankrupt yourself. It's like, think back to these 200 million IBlinks a second thing. Like, if you do that many trades, you can just be bankrupted in a second or two if you do the wrong trades. So you somehow need to also monitor this and make sure you don't go bankrupt that fast. That's like super important. I think at Optiver, we're like, this is one of the things we value the most. Like, we take risk extremely seriously, and everything we do is sort of built under this umbrella of a risk system that makes sure that we do safe things. And then pretty much like this is stuff that's in the data center itself. And then so we have like main control servers that control the whole operation. Like in some central data centers, we have data collection services that just monitor what's going on, collect data that we then crunch through later and do data analysis on. You have GUIs, of course, traders use to control their systems. And then we have like in the cloud, like all sorts of data analysis and research infrastructure that we use to compute, to do various analysis. Does it make sense, roughly? Are there any questions or? All good. So I want to talk a bit about sort of what I do as a software engineer at Optiver. So I sit in between, I would say, the more like technical roles, like people building these FPGAs and building these highly optimized trading systems, and people like traders and researchers who sort of have a more of a holistic view on our operation and don't care so much about the latencies, but just look at what's happening in the market. How do we react? Elon Musk tweets something, what do we do? And so we as software engineers, we sort of, on one side we get to see the technical things, but on the other side we also get to see the business and how the trading really works, and we sort of combine both. We form a bridge between sort of this technical, like super technical world and the trading world. And I think it's really exciting because you get to have one foot in both of these worlds. Right? The people here, they don't care so much about what's actually going on in the markets. They're just optimizing trading systems. So I enjoy this a lot. That I get to do both. I think that's pretty fun. Yeah, that brings me a bit to the future of trading, let's say, or the future of what we see as the future for us. And that is that, so we're in this race to transmit information, ultimately, like us and our competitors. And whoever has the most competitive systems is at the front of this race. And so we're always in search of new opportunities, both in markets but also in technology. And I think the exciting thing is that we're always sort of shooting for this moving target, right? So things are always moving. Somebody invents a new thing, and now we need to react. And then a strategy didn't work. It worked a couple of months ago, and it's super dynamic. It's really like a video game, or like a bit like what you guys are doing with our challenge. So what that means is that we're trying to do what we do now, but scale up massively. We want to do it 10x or 100x more. We want to do this while not losing, speed or smarts. So we want to maintain where we are now or get better. But pretty much we want to just scale up without getting worse. And I think that's a massive challenge. And that's pretty much what we're trying to do. That's also I don't know if there are any questions. Yeah,
it's possible that you can lower the most latency currently.
Is it possible?
Yeah, it's possible that you just reach the physical limit with the FPGAs.
Yeah, it's a good question. I mean, so we asked this question as well. I think the answer people say is like 10 years ago, people were asking the same question. They were like, is it possible to go faster? And we're like, nah, it's not possible. And then we went faster. So I don't know. I would say no, but at some point you reach the physical limit, right?
Where's the choking point right now? Where's that you can even go faster? Right now, it's like.
I don't know the exact. I also don't know if I can tell you, to be honest. These are a bit like, I kept it a bit high level. The exact details we usually don't share so much. But what I can tell you as well, though, is it doesn't matter so much on speed. It matters more also on sort of how exact the exchange is. There's a lot of variance in the exchange. It doesn't matter so much being fast, right? Like if they apply to you with like a 10 microsecond deviation every single time, it doesn't matter that much. But if they're super precise, and everybody gets their reply to the exact nanosecond that you can predict, then it matters a lot more. And at some point, you get to this point where just like there's so much variance that it doesn't matter that much to optimize even more. And then you better focus on something else.
like in the smarts part, like
Yeah,
you were
exactly,
saying.
yeah.
Okay.
But to me, to answer your question, you'd have to talk to one of our sort of more partners people.
I'll look at how
That's definitely hard, and I don't know what the bottlenecks
So
are.
you're now more in software, you're more in the part of the scaling up modes, like the 2, 1 or 2 orders of magnitude.
Yeah, yeah.
Okay.
Right, for software, it's mostly we want to trade more and do it more efficiently as well.
Okay.
Yeah. Any other questions? Yeah?
I have a question that I always
Okay.
from the, maybe it's not your data, from the, for example, the study series side, with these vast amounts of data coming in and out, how is it sure that the market can sort of choose what stays consistent within their own servers? Because I guess there's a lot of parallelization when it comes to
So you mean how does the exchange make sure that
that they're not saying something to different people at the same time, for example.
and what's exchanges? You mean exchanges or us?
Exchanges.
Because exchanges don't really sell anything. Oh, you mean like that? You mean? No. Yes.
Like maybe you're interested in buying something someone else's, and I'm interested in selling something that maybe you can
So there is other parallelization, but it all comes down to a single point. So they don't the exchanges will not have two parallel points where they sell the same thing. Like for one single product, there can only be one thing.
So you have to connect to just one computer, like one single server, which is running.
No, like you can connect to multiple, but what happens is that they take they're called gateways, and then pretty much they timestamp every message. But like once you've timestamped it, you can be slow on it, right? Like then you know you can order it yourself, and you can collect all the data from all the different computers, and just like merge it, and then have like know which one came first.
So then it comes to just, all the gateways, like sort of being in sync and making sure that if something comes here before it comes there, and the timestamp.
Exactly. Well, so let's say something comes here at the same time, but this one is slightly faster, and this one will get it. But in the end, it all gets merged together in the same computer. And then one process will look at all the orders. But that can be slow, right? That can happen milliseconds later. It's all about the initial entry point to the exchange.
So like, then the science becomes the synchronization of the blocks between the seconds.
That's definitely part of the drone data. So then what we also do is very good question. It's called droning. So when you send multiple orders at the same time to all these different gateways, so that you hope that whichever one gets it first will get your turn.
Which is the learning path would be software engineering, because I suppose you have to know the basics in math and but once you have already all the general knowledge, in which part have you go deeper? It would be
I think that depends on. Honestly, I don't think you don't need to know anything specific. I mean, I just studied normal computer science, and then I just applied, and they took me like you could just apply. Like there's no special knowledge that's required. We sort of teach you on the job. That's our philosophy. And then what you want to do is a bit up to you. I think there are various different problem spaces. Like let's say you're interested in sort of building these trading systems. That you could go into those teams. If you want to more work on sort of like the pricing or pricing research and figuring out how like algorithms to compute fair prices, like that's a different thing. And you could go to that department. So that's a bit of what you want to do. But I think there's not really like you don't need to know all these things before. Like I definitely didn't, and most people don't. You just kind of learn it. Yeah. Wow, that's it. Yeah, thank you for your sorry, one more question.
I understood consider is marketing.
Yeah.
So a marketing maker, when you research that I read, I use this day, does not like does not invest in the stock.
Yeah.
I mean, it just like makes profit from the difference, the spread. So when you say that if Elon Musk quits, we have to do something about it. Why you?
Nah, that was just for the story.
Okay,
Like,
okay.
we don't do this ourselves, but it was more to tell us, because I think, I was thinking maybe it's more relatable for people in the audience.
I just.
I have one more question as well. With this whole arms race of becoming, the fastest or the less latency when it comes to responding to the market. Are there considerations of whether this is just I don't know, creating more like side effects, like environmental side effects, or like in terms of costs for all of you, and maybe like if you just got all together and said let's just trade every second, maybe it would be better for you. So are there any efforts, maybe not in that direction, but in terms of trying to lower the costs for everyone?
There are some discussions in the industry. Like, I think the thing is, if you're just you need a fundamental change in how the system works. So instead of having these sort of instant orders that you can send, like one idea that people have is like micro auctions, where maybe like every half a second orders get matched.
But like then if you just match them every quarter per second, you become rich with that just doing it.
It gets, so that's the problem, right? It gets tricky. Like whatever system you have, there's something that you can do to exploit the system, and you need to come up with a system where you can minimize this. Just the way the current system is built, like it leads to this type of behavior. I think it's a bit of a side effect, but yeah, it is how it's kind of what you have to do to play the game. If you don't do this, you cannot play the game. But yeah, there are definitely some discussions ongoing, like what can changes do to change the way these management.
So it's just the way you phrase everything, it sounds to me like a bit like what was happening with GPUs and Bitcoin and all that sort of stuff. Like maybe it's getting too competitive to the point where it's costing a lot of money to a lot of people and not sort of environmental side effects.
I guess the thing is, we're a little bit small, right? We're like 1,000 people. I don't like, and the cost are on ourselves. It's our own money in that sense. In the environment, we have maybe like 10 computers in one data center, like somewhere. So it's not like we have massive.
No, I was not using
So I don't think we have companies like us have a very big impact on the environment because it's just not big, compared to like any other industry, like maybe like 1,000 computers in total. It's not kind of make a big difference. But in terms of the sort of amount of money that gets invested into trying to understand this, it's insane. Like it doesn't make sense to spend this much money in trying to understand like how can you do it in nanosecond or 5 seconds or whatever. Like there's no value in it, right? Well,
You're more competitive.
you're more competitive, but like ideally there shouldn't be, in my opinion at least, the system shouldn't be designed so that you're incentivized to do this. Right? Like if you're a doctor, let's say, like if you spend more, like you take the same money and you allocate it to like doctors or whatever, that's a much better use of the money, right, for society. I think like that's at least how I see it. Like that's the dilemma more. I don't think the environment. I don't think we're not that big. It doesn't really impact the environment. Yeah.
And the capacity that a company like Fortiva has to let's say the prices like in so much in that amount of time to make it. And it doesn't make you like a good company to invest in stocks because you have like an advantage, you would say, against other.
No, really. Let's say if you have an advantage, that would be called. You can trade on that. That would be considered insider trading, and that's illegal. And you can't use any information you have that others don't have. Well, not for your own private investment. That's like a big. So pretty much, if you work in this industry, there are a lot of things. There's a lot of compliance, a lot of monitoring. You can't just do whatever you want. I don't think so. Any other questions? Should we wrap up? Well, thank you very much for coming. I hope you found it interesting. Oh, I don't know. I guess we'll just stop this. But yeah, there's definitely some. I mean, there's some exchanges that are trying to explore this micro option. So instead of continuously trading, like every 10 milliseconds, they just match the orders. So maybe that will, maybe that will happen. I don't know. There are
Otherwise, like some exchanges that are less like same thing.
There's no, I mean, the exchange is not like the exchange is just a place where you do the trade. And they don't do it, they don't invest, they don't trade themselves, they're just facilitating trades and happening. I think you as an investor, you should be positive investing every second, half a second.